2065 maximum path quality of the graph. Let's see. So there's an undirected graph with n nodes numbered from 0 to n minus 1 inclusive. You're given a 0 indexed integer array values, where values I is the value of the ith node. You're also given a 0 edges array, indicates it's a weighted graph where there's time j seconds to travel between two nodes. Okay. Finally, you're given an integer max time. A valid path to the graph is any path that starts at node 0 and ends at node 0, and it takes most max time seconds to complete. You may visit the same node multiple times. The quality of a valid path is the sum of the values of the unique nodes visited in a path. Each node's value is added at most once to the sum. Okay, return the maximum quality of a valid path. There are at most 4 edges connected to each node. So this seems very difficult. I'm getting some exponential vibes from this problem already. Like, this is going to be something that is not efficiently solvable because I need to enumerate all paths and I need to start at one place and like go all around and come back. So that sounds very traveling salesman-ish like. And the fact that it says there's most 4 edges connected to each node, it's like you're specifying that there's a few edges intentionally because this thing probably is not efficient to solve otherwise. I mean, it would be too slow if there was too many edges. And yeah, like, so if max time is 100 and each time is greater than or equal to 10, then I can only travel to like 5 nodes. Anyways, right? So since I have to go out and come back and I only have 100 seconds and everything takes 10 seconds to get to at least, then it's going to be like 5 seconds total. Right? I mean, 5 nodes that I can travel to anyway. So this solution is, even though it's going to be really inefficient, there's really tight constraints on what I can do. So it's not a big deal if I do something very inefficient. So I guess the only hint here is, sometimes these problems will describe the fact that there's an inefficient solution unintentionally because it says things like there's almost 4 edges, and then you look at the constraints of the values and you see that they're all kind of bad. So let's just try to do just a simple DFS and see if we can get the maximum solution. So there's some weird aspects of this problem that we're going to have to think about. First, let's convert the edges to a graph. So we have a graph. For range length of values. So I'm trying to convert values. The length of values will tell you the number of nodes. And then for UV weight in edges, graph at U append VW, and graph at V append UW. Okay. So let's go ahead and draw this out. So this is 10, 15, 10, 0, 43, 32, 10. So we can enumerate all paths in this graph here. The thing that's kind of tricking me is how are we going to make sure that when we go down a path and we come back, we don't double count these values, right? Because we don't want to count the same thing twice. If we've already collected that information, then we can't recollect it. So maybe okay, so maybe when you traverse a graph, you collect the points, you set them to 0, then you finish, and then on your way back, you set them back to what they were before you started. So the basic idea, if that doesn't make sense, my drawing is you go down a path, you get to a node, you collect the value, and then before you continue, you set it to 0. And then when you're done continuing and you return, so like your recursive call finishes, you set it back to its initial value, and that'll make sure that you don't double count at all. Now, there's potentially going to be paths in this graph, right? Because there's going to be tons of non-valid paths. So like, for example, imagine that this system just kept going like this way forever. Not forever, but it just keeps going this way. Right? And maybe these were all like 10, 10, 10. And you get a fudge ton of points for going down these links, right? You get 100 points, 100 points, 100 points. So you might have a system that's inclined to keep going this way, but it only has 49 seconds to get back, right? So here it's already spent 10, 25, 35, 45. So at this point, there's no coming back. So we need to make a situation where if you run out of time, you return float infinity, negative infinity. You say, like, this path is not good, this path is bad news, you're not going to be able to find your way back. And only paths that find their way back to 0 get accumulated to the solution. Okay. So that's as much as I can say just generally. There's probably little tweaks we're going to have to make to DFS because there's kind of convoluted constraints on this problem. Okay. So we created this. And we'll run DFS on U. Okay. We'll have time left. So if time left is less than 0, we return float negative infinity. Right, so if you get somewhere where you ran out of time and you're not at 0, then you return negative infinity, meaning that this is not a valid path. Otherwise, you have more time. So confusing. Okay. Now somewhere in here, we're going to want to run DFS. So for V and G of U, so for each of my neighbors, I'm going to want to run DFS on V with time left, or V W for the weight. Minus W. Okay, and then this is where this idea we want to save the old value. So old value equals values at U. And then values at U equals 0. Old value. Then after you're done, you set values of U back. So best solution negative infinity. So I'm trying to save information about the best solution each time we run. Now, how do we get it where if it gets back here, so we need to have a case where, how do we ensure that it stops at 0? So we know it starts at 0 because we can just run DFS at 0, starting with max time left. So we need something like if u equals 0, yeah, but it could be a case where I can go out, go back, go back, go out. So I could pass 0 multiple times. So how do I know this is the last time I can reach 0? Best solution equals max. So if the best solution, after I run it on all my neighbors, this is bad, man. This is hard. Then you just return values at u. Damn, this is fucking hard as hell, dude. So I run DFS. So I'm gonna make a weird case here, and it's probably not. So if u equals 0 and all yeah, but that might not be the case either. Problem is I can't consider edges. Okay, so the only place it can run out. All right. Invalid syntax. Gotta have commas. All right, let's try that. And then I'll explain it if it's right. But it could very well be wrong. My intuition tells me it's right, but maybe it's too slow. Come on. Time limit exceeded. Damn! All right, is there a way to further constrain this so it's faster? All right, so this passes barely, but maybe it's one of those things where it really depends. Because this is where little heuristics are going to improve your runtime, because the runtime is really constrained because the system is really constrained. So small heuristics will probably make a huge difference. Like I could probably cut the runtime in half if I made a decision earlier that this path is not valid, right? Right, like okay, so is this thing a tree or is it always a graph? Okay, it's just a graph. Yeah, because you can't make any like I wanted to think about the fact, could I make a statement about if I'm too far out, there's no way back, but if I'm too far out, there could always be a path that's shorter that could get me back. But I don't know. This gets accepted and it passes. The idea here is the only place where you can stop is 0, right? So the only place where you can stop and not find anywhere else to go is if you're back at the source of 0. So that's what this is saying here. It's saying if I check all my neighbors and none of them are able to provide me with a valid path, then the only place that can occur is at u equals 0, right? Because that basically means it's stranded, right? This statement here is saying I'm stranded, right? I checked all of my other solutions. I checked all my edges going out, and none of them were able to provide me with a path, right? So I can't get stranded here. I can't end up at 2 and then be unable to find a path back, right? The only place where I can end up stranded is the destination. So that's what this is saying here. This idea here, this old value, new value thing, is just a swapping mechanism to ensure that we don't overcount the same node over and over again. This is just to make a basic graph. So, perhaps I could make this thing just a little bit prettier, but so let's make this a little bit better. For VW and G of U. So we don't need this best solution thing anymore. All right, let's clean this up just a little bit more. Okay, if max is an empty sequence, then the default is float negative infinity. Ooh. All right. Sorry, guys. Keep messing up. Well, that's going to ruin my runtime even more. Because now it's creating this list too. Yeah, well, it's only 4 elements. Let's see what's going on. Okay. See, that's why these problems are kind of bullshit. Because something will pass, and then you make a slight tweak that doesn't really change the runtime, and it's still, and then it doesn't pass. So it's like, you know, small things you do can cause you to pass in problems where there's, you know, total inefficiency in how it works. But that's the gist of the problem. So I'll look up to see if there's any other heuristics that I missed, but this passes, so it's good enough for me. Thank you.